Hello everyone, welcome to this webinar. I'm pleased to present you one of the new features in PTV Visum, the simulation-based assignment, short SBA. My name is Anett Ehlert and I am part of the product management team. This webinar will last approximately 50 minutes. You can use the chat functionality and ask questions during the webinar, and we will answer either directly after the webinar or later by email. Today's webinar covers several topics about SBA. First, I would like to answer the question why we introduced a new assignment in Visum. I will explain in more detail how the simulation-based assignment works. I'll talk about the requirements for network modeling, in particular junction modeling, and we go through some of the parameters, especially focusing on those for calibration. And in the last part, we will look at one example and see what results are produced and what type of evaluations are possible. So let's start with the question why we implemented yet another assignment and how this assignment fits into the hierarchy of different approaches. So first, let's take a look at existing types of assignments. The most basic and often used type of assignment for strategic modeling is static equilibrium. And in Visum we have path, link and bush-based methods called equilibrium, lose and luce respectively. As they are static, these methods assume what is called a steady state of traffic, which means that everything is a kind of fixed throughout the assignment period and over one or several hours, or even a whole day in some cases. So static assignments approximate node impedances, usually by using a volume delay function at the link, turn, or node level. Consequently, the interactions between vehicles of different turning movements are neglected. So these methods are popular because they are easy to understand and require the least development effort. Assignment with ICA is a special static assignment method. It combines ICA, intersection capacity analysis, a method for calculating detailed junction performance based on the HCM with static assignment. So this method is more precise than other static methods and can provide some information on time dynamics, such as queuing, but it is still based on the idea of a steady state, and though there is a limit to the level of precision we can expect. So we then move on to existing dynamic assignment methods in Visum, which explicitly consider how traffic evolves over time. The two current variants are called DUE and dynamic stochastic assignment. While these methods can explicitly consider the evolution of traffic and congestion over time, junction performance is approximated using fixed capacities for turning movements. So as you can see, there is a need for a method which assesses both detailed junction performance and time dynamics. So this is where the simulation-based assignment fits in as the most precise assignment method to ever be implemented in a macroscopic modeling platform. So SBA combines detailed junction performance and time dynamics in one dynamic assignment. So here we have a look at dynamic or quasi-dynamic assignments across different products, namely Visum and Visum, and see how SBA fits in there. So SBA is a dynamic assignment, dynamic as opposed to assignment with ICA, which is sometimes called quasi-dynamic because of the ability to model blocking back with queues and congestion. So generally, dynamic introduces a higher complexity. The efforts for data collection and calibration increases, so modeling errors can have drastic effects on the results of the assignment. In SBA, a simulation is used as opposed to other dynamic methods in Visum, which are based on analytical approaches. Simulation provides greater precision because individual vehicles are moved through the network. More precision is needed also for junction coding because precise signal plants are taken into account. So this also allows to take into account the effects of signal coordination and platooning. So I will demonstrate this using two very small examples. So the first one shows the effect of signal coordination. So here we have a tiny network, which is a stretch of road, and the demand is 1,000 vehicles in 30 minutes driving in the eastbound direction. 3 signal-controlled junctions exist on consecutive nodes, each 2 kilometers apart. So in this model now, the 3 signals are not coordinated. That means the time offset is 0 and the cycle time is 60 seconds for all 3 signals. So now I run the assignment and you can see different link attributes at the network. Volumes, travel times, delays and queues are displayed. So the values are per time interval, so we can move through the time intervals. And you will see that during the assignment, queues exist in front of all 3 signals, and also vehicles experience some delay also in front of the second and the third signal. So now I will change the time offset and I will introduce signal coordination. So basically I move the green time start by moving this bar in a way that the green line are in line. So I will do that for the second signal and I will do this also for the third signal. So basically when vehicles arrive, the green time starts. Now I will rerun the assignment, go back to the start of the assignment period, and here you can already see that the queues are disappeared and also the delay in front of the second and the third signals are also disappeared. So this shows that the time offset can have considerable effect on the results of the assignment. So in the second example, this example demonstrates the effect of different arrival patterns. Also here we have a tiny network. There are 2 origin-destination relations. The major flow direction is from north to south with 1,000 vehicles, and the minor flow is crossing in the west-east direction. Here the demand is 500 vehicles in 30 minutes. So this node here is yield controlled. As I said, the major flow goes from north to south, and this node is signalized, but the signal is currently switched off. So what happens now? So if I run the assignment, you will see that the 1,000 vehicle approximately move from north to south, and this will be a continuous traffic stream. So for vehicles who would like to cross here, it is difficult to find appropriate gaps to do the crossing. So basically there are only 175 vehicles on this link and they experience quite a long delay of 80 seconds. So now I will change this node to a signalized node. Basically I switch on the signal and we can see here that there is a cycle time of 90 seconds and half of it is the green time. So this of course will change the arrival patterns of vehicles moving from north to south. So what happens now is that there is of course a small delay in front of the signal, but here for the vehicles of the minor stream they experience much less delay and more vehicles are able to cross here. So this shows the effects of platooning. So how does SBA compares with the mesoscopic simulation in Visum? Both assignments use the same method for network loading, but still SBA can handle bigger networks with faster runtimes than the mesoscopic simulation in Visum. SBA in Visum is based on the macroscopic data model, and outputs are suitable for analysis in Visum. This, for example, includes detailed link analysis and also skim matrix calculation. The resulting paths are shown in the list with their corresponding attributes. So because of the similar nature of the simulation, SBA can be regarded as a useful stepping stone towards Visum. Visum, on the other hand, is more expressive. More detail can be taken into account. For example, you can model lanes and their properties, or also vehicle-actuated signals. Visum enables micro and hybrid simulation too. So consequently, you are often faced with the question, what assignment should I use? So the main question here is, what is the objective of the investigation, and can I answer the question of these investigations with a model at hand? Creating a model is not an end in itself, but serves a purpose, namely to answer certain questions. So subsequent to this, you may consider the following. For example, the availability of existing models that can potentially be developed further. The size of the model may play a role, and also runtime requirements. Also for the investigation, it is important to decide about the detail that is required to answer the question. Also related is the question, is the model in Visum the end goal, or are there further investigations in Visum planned? And also the assignment technique might be a question. Is an equilibrium assignment required, or can stochastic assignment be used? This can play, for example, an important role when comparing scenarios. So this also brings us to use cases for SBA. SBA is ideal for use cases with heavily congested urban and interurban networks, where oversaturation and queuing is present at different times and in different places of the network. SBA is ideal for modeling networks with transient congestion effects, which basically can lead to route choice that varies during the assignment period. It is also the assignment method that allows modeling of time-varying policies. For example, if you have speed reductions over certain parts of the assignment period or different tolls. It allows modeling of incident and road network effects and also traffic management. And to some extent, it is also possible to model the extent of evacuations. So looking at the assignment method, we will start with the basic principles of this dynamic assignment and move then on to the details of the simulation. Simulation, of course, is something new in Visum. So I will start with the flow chart of the procedure. So as I said, the assignment method is dynamic. That means the assignment period is divided into several time intervals. This also means that impedances have a time preference, and then the assignment starts with the shortest path search. This search gives paths for each time interval. Then the demand is distributed or redistributed to routes, and also this is done per time interval because demand and also impedances of paths can vary over time. So during the simulation, individual vehicles move through the network on their assigned routes. This step provides new travel times and subsequent impedances are updated. So convergence is checked and the steps are repeated if the gap that determines convergence is not met and otherwise the assignment terminates. So the simulation-based assignment is an equilibrium assignment, and as for static assignments, this means a traveler won't be able to improve his travel time by changing route. But here the condition applies per time interval. So to put that in other words, vehicles departing at the same time between the same OD pair but taking different routes must have the same experienced travel time. The impedances of all routes of an OD relation are basically nearly the same. So how are the impedances calculated? According to the definition in the general procedure settings, impedances can have different components, among them travel time, to which a coefficient is applied. Additionally, time-varying attributes take effects. They represent the changes of the supply side during the assignment period. So how are travel times determined? This is the main purpose of the simulation, to determine travel times in the network. So travel times are measured over short time intervals. The duration of these intervals is a user-defined parameter of the assignment procedure. Furthermore, travel times are measured for links separated by turning direction. This, of course, is more realistic because queuing effects for certain turns, for example due to insufficient flare lengths, are taken into account. So we can see this in the picture on the bottom right. There are vehicles queuing to turn right, but the vehicles moving straight are not affected. So their travel times on these links are faster. So once the travel times are measured, we can derive travel time functions. We can see one function, for example, for a link with a specific turning movement. In this example, it is assumed that travel times are measured in 5-minute intervals over an assignment period of 30 minutes, followed by an extension period. So the horizontal bars over the measurement intervals show the averages, which also represent the travel time in the middle of these intervals. The average travel times are then interpolated to form the curve, the dashed line. So that means at each point in time we know the travel time for this specific network object. So these travel time functions are then used during the shortest path search. Again, as I said before, this is done in each time interval and also during network balancing, where route impedances based on experienced travel times are also used. So now we look at the simulation. The simulation is used for network loading. The basis of this process is the mesoscopic simulation, which is also implemented in PTV Visum. The simulation uses a simplified curve following model, which is also in which braking and accelerating is neglected. There is a simple model for lane selection that basically ensures that vehicles can stay on their route. And as a consequence, junction modeling, including control and geometry, is required for the simulation. So for the curve following model of the simulation, 3 parameters are required: the free flow speed, which is a link attribute, the standstill distance, and the reaction time. The latter 2 are defined for each transport system. So for vehicles, we distinguish between 2 different states. Either vehicles travel at their desired speeds, or they follow the vehicle in front with a headway equal to the reaction time. Here the effective vehicle length is regarded, which is composed of the standstill distance and the vehicle length itself. So because in SBA a simulation is used, the capacity is not an input attribute, but can be calculated from parameters of the following model. So more precisely, using the effective vehicle length, the reaction time, and the free flow speed, the capacity of a link is calculated and is displayed as a calculated attribute in, for example, link listings. So in Visum, lanes of a link have still the same properties. That means free flow speed is identical for all lanes, and also the same set of transport system that is permitted on the link is allowed on lanes of the link. The options for lane selection is derived from the junction geometry. So lane selection occurs when a vehicle enters a link. More specifically, a vehicle can only select a lane from which the next link of the route can be reached without the need to change lanes. So let's look at the example, the intersection here displayed. So coming from west, turns in all directions are possible. A vehicle that would like to turn right needs to use the right lane. A vehicle that would like to turn left needs to use the left lane, and to move straight, all lanes are possible. So the selection is then made based on macroscopic quantities. Then, as I said before, the selection occurs at the upstream node of the link. So moving on to junction control. Junction control between conflicting traffic streams is modeled using signals and gap acceptance. For signals, the exact signal times are considered, the green start and the time of green end. So, and as we have seen before, the offset can make a difference. We have seen that in the demonstration example where delay varied considerably depending on the offset. Conflicts between different traffic streams are derived from the major flow definition and the junction geometry. So for assessing junction delay in give-way situations, the three following parameters are required: the critical gap, the follow-up gap, and the maximum wait time. The meaning of gap values follows the highway capacity manual definition. So, for example, the critical headway is defined as a minimum time interval in the major street traffic stream that allows intersection entry for one minor street vehicle. So it determines how the capacity of the minor stream decreases when the volume on the major street traffic stream increases. So the time between the departure of one vehicle from the minor street and the departure of the next vehicle using the same major street headway is called follow-up headway. So this headway or follow-up gap defines the saturation flow rate for the approach if there were no conflicting vehicles on movements of higher rank. So the picture on the right show default values for these gaps. For the minor approach from south, the values depend on the major flow direction, here east-west, and on the ranking of movements. The maximum wait time is a global parameter that describes the behavior at junctions when sufficient gaps are not available. So for example, the major traffic stream is operating at capacity and vehicles from the minor stream need to squeeze in here. So this brings us directly to the requirements for setting up a model for SBA. We look at the requirements at the level of network modeling, junction modeling, and finally we have a look at parameters for calibration. So first, the permitted transport systems for links, turns, and connectors are needed. For links, the free flow speed and the number of lanes need to be defined. Because a simulation is applied, capacity is not an input attribute. So that means this link attribute is ignored when a simulation-based assignment is executed. Junction control, there are basically two components, signal timings and gap acceptance. The right-of-way is essentially determined by the control type, and for two-way stop and yield controlled nodes, also the major flow direction is needed. Junction geometry, this essentially is concerned with the lane allocation and the definition of flares, including their lengths. Then there are the new parameters, the effective vehicle length and the reaction time. This is needed for the car following model, and the maximum wait time for junction operation. Temporal distribution of demand is modeled. This can be done either by using time series or a set of matrices with time information. Supply changes can be modeled using time-varying attributes. So they can be used to define temporal changes of the supply side, like in this example, there is a speed reduction over a period of 30 minutes. So for junction modeling, what exactly must be modeled for SBA? So for SBA, all nodes must be represented with their junction geometries and have a control type. So more precisely, one needs to define lane turns within the node, and from this information, conflicts can be derived. There are two types of conflicts. Lane turns can have the same destination lane, or second, they cross each other. So in SBA, depending on the control type and ranking of movements, standard values for the critical gap and the follow-up gap are set. The basis for these default values are well-known guidelines like the Highway Capacity Manual. So if these values are not applicable, they can be overwritten by the user. And also offsets of signals are considered and determine waiting times of vehicles if they pass several signals on their routes. So what parameters must be defined for SBA to run an assignment? There are first the termination criteria, the gap, and the maximum number of iterations. Then a random number is needed for the simulation. Under assignment time intervals, the assignment period as well as the analyzed time intervals are determined. And furthermore, an extension period is needed. During this period, all vehicles must be able to leave the network. So under path and balancing, the time interval for averaging travel times from the simulation is defined. The path search can be restricted. This can save time, but we would not recommend to do so. For network balancing, there are two options. With MSA, volumes are redistributed to the best path, and with cost proportional, volumes are redistributed to paths that have cost lower than average. The amount of volumes that will be redistributed decreases with the number of iterations. So for longer assignments, for example, if you would like to model a day, we would also recommend to make use of options for time interval dependent control, which is not shown here. So now we move on to the question of how to calibrate the model. So first of all, it is important again to note that any error in modeling has more drastic effects in dynamic assignments than in static ones. For example, this can result in grid locks. So therefore, we would strongly recommend to first model the network correctly, and then you can start calibrating the model. To do so, you can use the fundamental diagram. The fundamental diagram shows the relationship between macroscopic quantities such as flow, speed, and density. Here in the example, density in vehicles per kilometer and lane is shown on the x-axis and flow and vehicles per hour on the y-axis. So it is very convenient that one can use the parameters of the curve following model to describe properties of the fundamental diagram. So the formulas for the macroscopic quantities are shown on the slide. So the critical density is the point where the flow starts to decrease with increasing density. The maximum density can be calculated using the effective vehicle length, here named with lambda. And the maximum flow also depends on all three parameters of the curve following model, namely the reaction time, the effective vehicle length, and the speed of the link. Why is this helpful? Macroscopic properties can be reproduced by setting the parameters for the simulation. In other words, there is no discrepancy between the simulation and macro modeling. So here we see where you can find the corresponding parameters in Visum. For global definitions, there are the parameters for the transport systems, the reaction time, and the effective vehicle length. And to make changes individually, for a link, for example, you can use the factors at the network object, which are shown here in the list of links. So I will quickly demonstrate the effect of these parameters. Here we have a stretch of road. Cars are here visualized for demonstration purposes. Cars moving from west to east, and there is a traffic signal where vehicles must stop. Now I will change one of the parameters of the curve following model respectively and start with the reaction time. Here we have different values for reaction time, and we can easily see that the speed of the shock wave that moves upstream is faster with shorter reaction time. The standstill distance, of course, this will have an effect on the maximum density and the number of vehicles that can fit into a link, and the speed, which is usually not a calibration factor, but here we can also see that the speed of the shock wave is different here, and also the maximum flow of the link will be different in these two cases. So for calibration at junctions, I already mentioned that default parameters for the critical gap and the follow-up gap are in accordance with guidelines like the highway capacity manual. Nevertheless, if these values are not suitable, you have the options to override them. In Visum, depending on the control type, parameters can be found at turns or at legs. For each time gap, you have three parameters. One is the bool value, which basically enables overwriting. With the second one, you can set a user-defined value. And the third one is basically showing what has been used in the simulation. So the parameters for gap acceptance, the critical gap and the follow-up gap can be calibrated against measured data. In this case, it may be useful to know the effects of the parameters. The graph shown is similar to the ones which is used in guidelines like the highway capacity manual, and it shows the influence of parameters on the potential capacity given the conflicting flows from other movements at the intersection. So in the highway capacity manual, for example, these graphs exist for different control types and different junction layouts. So how do the parameters affect the curve? So the follow-up gap mainly determines the intersection point with the y-axis. So it is basically the saturation flow if there are no conflicting flows. The critical gap determines the shape of the curve. Basically, it describes how the potential capacity decreases with increasing conflicting flows. And the maximum wait time determines the capacity of the minor stream when the major street traffic operates at the maximum. So far for the calibration. In the last part we move on to outputs and evaluations. So first of all, SBA comes with a list for the assignment statistics and quality data. As for other assignment methods, you can find information about convergence as well as overall statistics, like the total kilometers traveled or the total time spent in the network. Most attributes are also available for time intervals, which allow you a closer look at what happens during the course of the assignment. So now I will show you an example in Visum. So first of all, there are the standard attributes you know from other assignments like volumes, travel times, speeds, and they are given for each time interval. For example, link volumes, you can here move either manually or automatically through the time intervals, and you can see the values, how they change over time. Of course, these values are also available in lists, and as I mentioned, we have here volumes, we have impedances and travel time, and here again you can move through time and you can see the changes of these values. And there is also a new attribute which is the delay, and also this attribute is available per time interval. So because of the nature of this assignment, there are a number of new attributes such as SPA density, queue length, which is here measured in meters, and SPA utilization. They are shown here. And of course they can also be displayed. Here, for example, the utilization. The utilization is a scaled density to some extent similar to the volume capacity ratio in the static case. Volume capacity ratios, of course, cannot be used here because capacity is not an input attribute. So for the utilization, basically utilization of 100% indicates that over the time interval vehicles travel as close as possible with their maximum speed. So of course this also means that the utilization can get higher than 100% because at lower speeds than the free flow speed vehicles travel more closely to each other. And then there are also attributes from the simulation available. This might be useful during the calibration, or if you would like to have a closer look, there are attributes called simulation detail, and they show, for example, the vehicles entering a network object or the vehicles exiting a network object. With SPA you can also use flow bundle analysis. So as you know from other flow bundle analysis, you can select a network object, and additionally in SPA you can use a temporal restriction. So for example here I would like to look at vehicles which enter a certain network object between the 10 minutes I define here and then I run this, and of course at 6:10 I will not see any vehicles because I have restricted the analyzer to 6:20 to 6:30, but again in this period I can see the vehicles entering the purple marked link at this time interval. So apart from the link volumes, you have also the option to output matrices from the flow bundle. These matrices can be either departure time related or arrival time related. So we have also introduced a new procedure, which is the calculation of dynamic skin matrices. This can be used in combination with SBA, and also here you have the option of either getting departure time related values or arrival time related values. So this was the last part of the presentation, output and evaluations. And now I would like to come to the end of the webinar. For more information about SBA or PTV Visum in general, please check our website and the materials provided with the installation or demo version. I would also like to bring to your attention to other upcoming webinars. Tomorrow you can learn more about enhancements of the passenger survey module, and on 9th of March we will give you an introduction to 3D visualization in PTV Visum. If you have any questions on the topic or would like to share your comments, you can contact us. We will answer questions still in this webinar session or afterwards by email. I hope this webinar was of interest to you, and with this I would like to finish the presentation. Thank you.